Hello, AP Chem students, and welcome to topic 9.1, Introduction to Entropy. The learning objective for today is 9.1.a, identify the sign and relative magnitude of the entropy change associated with chemical or physical processes. So let's talk about entropy and microstates. So entropy is a complex idea that explains why some processes proceed in the direction that they do without being reversible. So for example, why can't you unburn a log? That's a classic example, or uncook an egg. So entropy increases as the number of microstates increases as well. So a microstate is the specific configuration of the locations and energies of the atoms or molecules in a system. So for example, we're going to consider this model here. I love this. This came from a LibreText article, and it's really, really good to help you understand microstates. So if we've got 4 particles and we're going to put them in 2 boxes, so you can see that. So we've got red, green, blue, and yellow particles, and we've got these 2 boxes. Each possible permeation is shown, and then they're grouped by equivalent particle arrangement. So for example, here's the possibilities, the number of possibilities of arrangements if you move just 1 particle into the second box. Here's the possibilities if you move 2 particles into the second box. Here's the possibilities if you move 3 particles into the second box. And then here's the final possibility, group of possibilities if you move all 4 into the second box. So each one of these groupings is called a macrostate. And so the macrostate with the highest entropy is the one that has the most possible arrangements. So macrostate A has 1 microstate, B has 4, C has 6, D has 4, and E has 1. So the macrostate with the highest entropy is grouping C, making it the most probable arrangement found in nature. Because if you just did this and these were randomly allowed to assemble themselves in whatever way is possible, it's going to happen to look like row C more often than it's going to look like the other permeations here. And so that's the idea behind entropy. And so entropy is actually just an application of probability. So once you take this complex idea and you scale it up to the level that is a physical change or a chemical change with all the different atoms and all the different ways in which energy can distribute in bonds, for example, or in particle movement, then you've got a situation where whatever the greatest amount of entropy is going to happen strictly because of probability, because any other arrangement is going to be basically insignificant when you take the probability of that occurring into account. So the entropy and therefore probability of the process occurring increases with increasing matter and energy dispersal. Okay, so back to that, the more we spread out the dots in the boxes, the more entropy we had. And so that is true of all of chemical and physical processes. The more possible microstates, the more probable it is that that will occur. And therefore, when we scale that up, that is what happens in nature. So for example, if we have ice and we have water, it's more probable that you're going to find this arrangement in the form of water. Now, that's not to say that you don't form ice, because of course we know that we do. And so that's where you have a balance of entropy and enthalpy. And that's what we're going to be working towards, I believe, in topic 9.3. All right, so, but let's just focus on entropy for now. So a positive value for entropy means that the entropy is increasing. Okay, and so we're going to think about it in terms of that dispersal, the dispersal of energy, the dispersal of matter. And because the dispersal that corresponds to your number of microstates. So here we can see that we have 2 moles of O3 gas, and that can convert to 3 moles of O2 gas. And so if we look at this, you can see we got 1, 2, 3, 4, 5, 6, 7, 8 molecules here, whereas over here we got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so 12 molecules are more dispersed than the 8 molecules. And you can see that in the picture. A negative value for entropy means that entropy is decreasing. So your dispersal is decreasing. So for example, in this picture, we've got solid magnesium and hydrogen gas. And then when they react with each other, they form this solid magnesium hydride. And so this is far less dispersed because it's a solid that's, you can see, rigid and has defined locations. Whereas before we had a gas that was present, and gas is highly dispersed. Okay, and there's your source for those bottom 2 images. So if we're going to evaluate the enthalpy change, if we think about states of matter, and dispersion, it should make sense to you that a solid is less dispersed than a liquid, and a liquid is much, much less dispersed than a gas. So if we look at it here, so a solid is pretty tightly packed. A liquid spreads out a little bit more, but a gas is way more dispersed than both of those things. And so your motion increases, your molecular interactions decrease, meaning that they can disperse more as well. So when you're considering a system that has a mix of states of matter, the side of the reaction with the greatest number of moles of gas will have the most entropy, period, done. So that's what you want to look for first, is moles of gas. Now, if we're considering a system that's all gaseous, and especially if you have the same number of moles of gas on both sides of the reaction, an increase in volume will lead to an increase in entropy. And so if we look at this picture, you can see that they can disperse around a larger space more, and so that increases your entropy. An increase in temperature will also lead to an increase in entropy, because this is more of a dispersion of the energy. So here the matter is the same, because your volume, especially if you're keeping your volume set, it's the dispersion of the energy that is present. And that's an application of kinetic molecular theory. The distribution of kinetic energy of particles of a gas increases with increasing temperature. When you consider a system involving dissolution, it gets a little bit more nuanced. And if you remember back from the last topic in Unit 8, when we talked about the free energy of dissolution, there's actually several different parts that you have to take into account, right? So the solute has to separate, the ions have to separate from each other, and then the solvent has to rearrange around the solute. And so generally, the solution will have a greater amount of entropy than the separated components, but not always. But if we're making a generalization, generally the solution has greater entropy. And so remember that nature proceeds towards the side with greater entropy, if all you're thinking about is entropy. Okay, so choose the species in each pair with the greatest entropy below. So I've got H2O liquid and H2O gas, 2 liters of helium gas at 298 and 4 liters of helium gas at 298, copper sulfate solid, copper sulfate aqueous, methane, and propane. So if you want to try this on your own, go ahead and pause the video now. I'm about to go through the answers. All right, so looking at the answers here, number 1 is straight up application of states of matter. So if we're comparing a liquid and we're comparing a gas, the gas is going to have way more entropy. Here, we've got 2 gases. They're at the same temperature, and so, but different volumes. And so in this case, again, we're going to look at the dispersion, and they can disperse more in a larger volume. And so that's going to have a greater amount of entropy. If we're considering a solid and aqueous, and we have no other information, then we're going to assume that the dispersion increases with the formation of the solution here. And then looking at the last one, if we've got methane and ethane, assuming that all the factors are equal, your energy can disperse more in a molecule that has a greater number of bonds. There's a greater possible number of arrangements of that energy across the matter. And so that's going to be an increase in entropy there. So you can see I forgot to mix them up. They're all, the second one has the greater amount of entropy. And that is it. So what should I be able to do with this? First of all, justify the sign of enthalpy, or it says enthalpy, that should say entropy. Hang on. Okay, there we go. Justify the sign of entropy or relative entropy values by examining the dispersal of states, meaning the number of microstates, and the number of moles of gas during a change. And then also discuss the impact of temperature on entropy. And that is it. Now we are going to talk more about quantifying the amount of entropy in the next video. So I'll see you soon for that.